So, today we are going to continue our conversation about vision. As I said, we're going to talk about vision for a long time, right? We're going to talk about vision for a very long time through the rest of the semester, mostly. Maybe the last 2 weeks we won't talk about vision exclusively, but we'll still talk about vision in some degree. So what we've done the last couple weeks is give you the background on the visual stimulus. We've given you some background on how your brain, your nervous system grabs those visual signals, right? Those waves and particles, and what it does with that, right? So now what we want to do is we want to talk about how we're processing those things. We're going to take each of these sort of channels of vision and break them down and talk about them differently. Now your book, these slides are actually from, I think, the second edition. The content's the same, but the guy moved this up to chapter 8. Does that make more sense for you who have the book? I know you all brought your book to class today, right? Like all 3 of you. And it happened as an accident for 2. So there we go, right? Yeah. So it's probably chapter 8. The reason he moved color vision up is I think it's easier for folks to think about color vision than it is some of the other types of vision. In the previous edition, he started talking about what we call spatial vision first. And the problem with that is spatial vision is a fairly complicated modality, right? And it's hard to talk about spatial vision before you've talked about color vision. Most people can understand color vision. If there is anyone in the class, and I think there are probably at most 2 people in this category, because I don't think you're in that category. The color vision, the color blindness. Do you have good color vision?
Probably not great.
It's probably not great. So if anybody does have a color vision deficit, we might figure that out later. So that'll be exciting. All right, so we're going to talk about different ways that you can mix colors, right? So we're going to talk a little bit about not just what your visual system's doing, but maybe the way you think about mixing paint colors, which is a different process, right? Not surprisingly, your brain and paint work differently. I know, right? That's a shock, but that's how that works. We'll talk about ways that you can look at colors, and we really want to think about this thing called a trichromatic excitation ratio. You're going to hear me say cone excitation ratio about 3 million times today. Okay, so cone excitation rate. Go and write it down. I'll give you 10 or 15 hours to do that, because that's how many times I want you to write it. Cone excitation ratio. This is one of the most important concepts I want you to take away from today. The reason I want you to take that important concept away today is because guess what's going to happen at some point in the future? I'm going to ask you to tell me about cone excitation ratios. Okay, this is going to be an exam question. I'm not going to try to pull a fast one on you and confuse you. I'm going to ask you, describe to me cone excitation ratios. That's almost word for word what's going to be on the exam. You can write that down. And if it's not just exactly like that, it'll be so close to it neither of us will remember. Okay? Because cone excitation ratios, I'm going to say it again, it's a little confusing at first, but once you get a handle on it, it makes so much sense. And it's very, very similar, if you remember, when we talked about taste, and we talked about the different taste receptors, and we talked about it being a ratio, right? How excited are they? How not excited are they? It wasn't just, oh, it's all salt. It's maybe some salt and some sweet, right? And so what are we getting on that ratio? It's ratios that are important, okay? So a great, how many of you are sports fans? All right, 1 person braving up 2 people. There we go. Well, we're getting into baseball season, so it's time to make all the baseball references possible, right? So if you ask somebody, who's the greatest home run hitter of all time, if you say Barry Bonds, you fail. I just want to let you know that's an instant F, so don't go there. So if you want to say, who's the greatest home run hitter of all time, right? And you might just say, well, whoever hits the most home runs is clearly the best, right? And that person's Hank Aaron. The problem with saying Hank Aaron's the best home run hitter of all time is that Hank Aaron was hitting home runs at a different time than other people were hitting home runs, right? And it's really hard to compare, let's say Hank Aaron versus Babe Ruth. Both hit over 700 home runs, right? So you'd say, well, they both have to be in the conversation. When Babe Ruth hit 700 home runs, everybody else was hitting 4. When Hank Aaron was hitting 700 home runs, everybody else was hitting 200, right? Still a big difference, but it's that excitation ratio, that difference ratio that makes a difference. And so hopefully you remember that great story when we get to cone excitation ratios, which I think we're going to talk about today, Wendeja, cone excitation ratios. Okay? We'll also talk about color constancy and color deficiency or color blindness. Okay? So why is color even important, right? Why is it important for us to be able to see color? And the reason for this is food, right? How many of you have ever eaten food? Yeah, right? Let's ask another question that probably has the same answer. How many of you have ever eaten food that was, let's say, not really fresh? Right? Okay? And sometimes it's a little tricky to know what's fresh and what's not fresh, right? But one of the best ways to do this is to look at things, right? And if we can look at something, we can tell if it's ripe or not, for fruit, right, in particular. So how many of you love bananas? I love bananas. There's always a big debate about when you should eat the banana. It's always when it has brown spots. I know so many people are wrong about this. That's the response I always get. If you're eating your banana and it has green on it, I don't know what you're doing, because that's a waste of time. That banana needs to wait 3 weeks before you even think about it. Okay? So let's think about that banana though, right? There's clearly a time when you can look at that banana, and if it's completely green, you know I'm not even going to be able to peel that thing, right? Because the peel's going to be too hard. And if you wait until the whole thing is brown, then you better be careful when you pick it up, because sometimes they're liquid on the inside at that point, right? And so you have to just scoop it into the trash. But somewhere in between is where you want that. Same thing for apples, for berries, right? Being able to judge the ripeness of food, right? Or even if you think about meat, have you ever seen rotten meat? Yeah, right? It's a little different color than regular meat, isn't it? Yeah, and you can tell, right? And you can tell when these things are not the way that you should eat them. Everybody's doing this face. Why is that? Thinking about rotted meat and curdled milk and big slice of moldy cheese and a rotten banana. Breakfast of champions. So, here's a particular sort of story which is really interesting. I don't know if you guys know Oliver Sacks. If you don't, you should get to know him. I mean, he's dead, but you should at least get to know his work, okay? So the interesting thing is this guy lost the ability to see color. Basically, everything was sort of like a gray color to him, or as he described it, rat-colored. So everything looked the color of a rat. And so when he tried to eat foods, they were really disgusting, right? Can you imagine trying to bite into a hamburger that's the color of a rat? A hamburger's not supposed to be the color of a rat, right? You're supposed to have that nice sort of golden toasted bun, good, thick dark on the outside, but nice and pink on the middle of the burger patty, right? Because you don't want to overcook things. Slice of yellow cheese, a couple red tomatoes, big leafy green lettuce, right? You have to leave off the mayonnaise because that's horrible. So there you go. That's colors, right, are important. So basically what this guy did is he just started eating foods that were black or white, right? So he would eat like rice or coffee or yogurt, things that were normally, achromatic, right, just black or white. He would eat those things because they looked normal to him, right? If he was eating yogurt and yogurt's white, he's fine with that, right? If he's drinking coffee, right, coffee appears black, he was fine with that because it matched what he was supposed to do, right? Sometimes, Josh, when you drink something that's not the right color, like Pepsi Clear, that's a long-running joke. Then it's strange. Has anybody had Pepsi Clear? Oh, it's an experience. If you close your eyes, it tastes like Pepsi. If you open it, it's a brand new experience. Because you're drinking that thing and it's like, man, this is some funky Sprite. So, color is important, right? I know a lot of schools will do like green eggs and ham days, right? For Dr. Seuss. I know, right? That's just gross. Who eats green eggs? And they probably don't taste very good. Even though there's not been a flavor additive, right? They just have a different color. We talked about this when we talked about taste. We said if they put red food coloring in something that's strawberry flavored, it tastes more strongly of strawberries, right? So there's that nice tie between vision and taste. So anyway, this guy lost the ability to see colors, and so he just started eating foods that were black or white because they appeared normal to him. Anything else didn't really look right. His wife even looked like she was rat colored. I mean, that just doesn't seem very appealing. Well, you got that nice rat sheen today. No. All right. When we think about light, and we've already thought about light a bit, we know that there's only this sliver of light that we can actually detect with our eyes, right? And this is not to scale. In fact, if we were to stretch this out over the length of like a football field, right, for this entire electromagnetic spectrum here, the sliver that you would be able to see, you can imagine that's like the thickness of the line marking the yards, right? That's the narrow band of light that you can see, right? This is very narrow. We can see from 400 nanometers to 700 nanometers, okay? Each of these wavelengths of light is perceived by us as a slightly different color, right? And so we want to think about sort of, yes, the colors, and typically we think about red, blue, and green, right? Those are sort of the three colors. But more importantly, we want to think about short, medium, and long wavelength cones. And we're thinking about that within that 400 to 700 nanometer range, right? So things that are short, that's on the 400 nanometer end. This appears blue. As you get closer to that 700 nanometer end, you start to see things that are red, and green is sort of right in there, close to red. It's closer to red than it is blue in terms of the wavelength of light. Okay? This explains why, how many of you have ever seen a sunset? Sort of reddish colored, right? The reason it's reddish is because as the sun goes down over the horizon, the atmosphere starts to stretch out those wavelengths of light just a bit, and as they get longer and longer and longer, they shift to the red. Okay? All right. Again, color is not really a property of the wavelength of light of the stimulus itself. It's what we perceive. Okay? All right. We've got this, what we call perceptual color space. I'm not going to ask you a whole lot about this, but you do want to keep in mind we sort of have four main colors. We're not thinking about bright versus dark here necessarily. If you were to try to describe most colors, you could break it down into about four pieces, right? Blue, green, red, and yellow. Okay. Most of the time we're not able to, we don't have other sort of segments in there. If we think about just the color of that, if we go, we try to break blue down, right? If you try to think about how would I describe the color blue using other, you can't, right? Blue's not a reddish green, right? It's just blue. It is. It's this sort of primary color that we would say. And this is true of just about every group of folks you're going to ask. It's going to break down in these four categories. Now, the interesting thing about this is I've already told you you really only have three sets of cones, right? One here, and one here. So how do we get that funky yellow? That's going to be an interesting thing we're going to talk about in a few moments. We're going to wire up a couple of these cones in an opponent way, right? And so we can measure. I remember saying something earlier about cone excitation ratios. Anybody remember that? We're going to look at cone excitation ratios, and that's going to give us that yellow. Okay? When we think about color, we want to think about sort of three main attributes. We want to think about hue, which is the primary wavelength. And that's not a great lambda, but it'll pass, right? So it's the primary wavelength. Okay? Is it a blue? Is it a red? Is it a green? Okay? That's what we're thinking about. In terms of saturation, we're thinking about how pure is it. Okay? If you think about the color pink for a few moments, that's clearly a red, right? But it's a desaturated red. Okay? It's a red mixed with a bunch of other light to make it pink, right? And that's how that works. So it's primary color, it's primary hue, right? The hue is going to be that primary wavelength, which is going to be in that red group, but it's not going to be fully saturated. Okay? And finally, we want to think about lightness or intensity. Okay? How bright is that source of light, right? So we're thinking about light. How bright is that source? Okay? Any questions about that? It's not so bad, right? there are two ways that you can think about mixing colors. There's what we call subtractive and additive. Okay, so let's briefly talk about subtractive for a few moments, and then we'll tell you why that's not what your brain's doing. But you have to know this before you know it's not what it's doing. So this is typically the way that we get when we mix dyes or pigments. So if you think about like paints, for example, if you're going to mix paints together, that's going to be a subtractive color mixture. Okay. And what we mean by subtractive is each dye that you put into that mixture is going to absorb a certain wavelength of light. Okay. So it's going to pull out a certain wavelength of light that's not going to get reflected back to you. Okay. So it's going to absorb that. So if you think about a dye or a pigment that's blue, for example, right, it is absorbing all of the wavelengths of light except what you're perceiving as blue. Okay? You can do the same thing with red or green. And intermediate colors have some mix of those pigments, right, so that they can absorb different wavelengths of light. So whatever wavelengths are not absorbed, that's what the color is going to appear to you, right? So when you're doing that. It's, again, very practical. If you want to, I don't know, make some tie-dye shirts or, paint your house, right? Thinking about what colors to mix together is going to be important. But it's not really good for thinking about how we actually process color, those color theories that we have, right? For thinking about how we have color vision, okay? And again, here's sort of that subtractive situation. You've got here a blue and a yellow pigment, right? Not too big of a deal. They absorb different spectra of light, and they reflect back what's remaining. And you've probably seen something like this before, right? Where you can have three sort of different colors, and you can use those to make, overlap and mix. Again, it's subtractive. So when you're looking at this section of the diagram, the wavelengths that are being absorbed there are everything but that particular green. Okay. When we do additive color mixture, it works a bit differently, right? So in this case, what we do is we add colors together. Okay, so we're going to excite different cones in different ratios. So we're going to have those cone excitation ratios at play here. And as we excite a different set of cones, we're not taking away a wavelength of light, we're adding in that perception, right? And this is actually how your like TV and computer displays work. Okay? So this is how that process works, right? So they're going to show different colors. So when you're wanting to see this color yellow, right, we're going to excite some red and we're going to excite some green, and that's going to give us that nice yellow color that's going to be coming out from that light source. Okay? And this brings up sort of a complicated concept called metamers. Okay. Additive color mixture will exhibit what we call metamerism. Right? It's a pretty simple concept once you figure out how it works. So basically you take one wavelength of light, whatever that is, pick your favorite number. You perceive that as a certain color. Then, let's say you take two other wavelengths of light and you shine those on the same spot, or on a different spot. Okay? Because of the way that additive color mixture works, we should be able to take these other two wavelengths of light and mix them together in a way that creates this same color that we're perceiving, which is the single wavelength of light. Okay? Does that make sense? It's kind of like, how many of you have ever been somewhere you had to pay $10 to get in? Okay, yeah. A lot of hands went up, just like $10 is a random number, but, $10 is reasonable, right? You had to pay $10 to get in. How'd you pay for that? Did you use a portrait of Alexander Hamilton? Or did you use 2 Abraham Lincolns? Could you use 10 George Washingtons? You see how you can add all of these things together and it still comes out to that $10, right? That's kind of how metamers work. Get really crazy, use a Lincoln and 5 Washingtons. What's really interesting is you could use 10 Washingtons, or you could use, I guess, 40 Washingtons. 500 Lincolns.
Or no,
1,000. Sorry, we were going into nickels. Well, we didn't make it to nickels. Didn't go to Thomas Jefferson, did we? I guess you could use 5 $2 bills. 10 cents to be Anthony's. All right. Josh, I'm glad you got a kick out of that. So there you go. So let's think about metamers just a bit, right? These are pairs of light containing different wavelengths that appear identical, okay? So basically, if you look at 2 circles, the color inside is going to be identical, but we made them in 2 different ways. One was just 1 wavelength of light. The other is 2 wavelengths of light that when mixed together appear that way, okay? If you have normal color vision, right, you can take these, you can take up to 3 sometimes, primary, and we're thinking about the red, the blue, and the green, right, or the yellow, and mixing those together, we can mix any 3 of those together to create any wavelength of light, or any, match that to any one single wavelength of light. And this makes sense because who remembers that time I said you have 3 cone types, short, medium, and long, that correspond to blue, green, and red, right? And so if you have normal color vision, you should be able to excite those 3 cone types in some ratio, right, that equals, you're going to excite them sort of individually or excite them like as a group with 1 wavelength of light, right? And it's going to appear the same, okay? What's interesting about this is once you've made this color, either by a single wavelength of light or multiple wavelengths of light, if you add a new wavelength of light on top of both of those that's the same, they'll both shift to that new color that's going to still be identical, right? So it's going to be additive, okay? So if you have $10, whether that's made up of Lincolns or Washingtons, and I give you 2 more dollars, everybody still has $12, right? So it's still adding the same. It doesn't make a difference. Questions about that? Okay. Always ask to be paid in Grover Cleveland's. So here's sort of how that metamer process works. For those of you that aren't aware, this is the international sign for an eye. Well, it's a little tricky there, so there's your eye. You're looking at these 2 patches of light, okay? They've not matched yet. Here's the test light, and then here are your 3 primary lights. And what you would do is you would either increase or decrease the intensity of each of these, right, and the mixture, so that this green patch eventually becomes the same color as that yellow patch. Okay? It's pretty exciting, right? If this is confusing to you today, it will be less confusing to you Thursday. Guess what we're going to do Thursday? We're going to do some color vision tests, right, which is going to be exciting. We're going to do some stuff that kind of deals with metamers, right, on the computer. There are a number of computerized tests that we'll take. We'll talk about those as we need to. Yeah, if you do have a laptop or a mobile device, that I think they can get it probably on a tablet. Yeah, a cell phone's probably not going to be helpful, but if you have a laptop or something to bring that into class Thursday would be great. You don't have to. We'll have access to this computer. We might be able to find another room where you can do that, and if some other folks in your group are responsible and they bring their laptops, you can use those. So now you have to wager out, like, am I the responsible person in my group or not? If you don't know, it's probably not you. Okay. Anybody seen one of these before? This sort of represents like all of the possible colors out there in the world. It's got this sort of coordinate system, right? This is really great for folks who are wanting to reproduce these colors for display purposes. If you're going to, mix some paints or create some signs or something. What's really interesting is this sort of shaded triangle, right? That is that represents all of the colors that can be created with sort of your standard 3-color ink set, right, that you get in your computer. So you always wonder why do I get 3, you get the yellow, the blue, and the pink, right? So those are kind of what magenta, cyan, and yellow. They didn't get fancy on that one. I always felt sorry for yellow in that case. Using those 3 inks, you can create all of the colors that are in that triangle, and that's a pretty good range of colors. I mean, it really is. It's a really good range of colors. You don't really need to go much beyond that. For most display purposes, you can get by with just what's in that range. Now, things are changing, right? As they make televisions that have better color producing technology, they expand what you get on your television display and so forth, right? Nobody's really excited about that. Your 4K televisions and various colors. Nobody's excited. I remember when those came out, they had George Takei as a spokesperson. Anybody remember those commercials? All right. Nobody knows who George Takei is. That's fine.
Original Star Trek.
Okay, that's better. Captain, he got a promotion. We have to keep things going.
Bent screens.
Huh?
Bent 4K screens. Talk about that? I don't know.
So I don't know enough about that technology, the bent screens. And that's a challenge. So bent screens have been a challenge for a long time, and there have been. So you probably think, like, why would somebody study vision, right, for their life? Well, the reason they did it is so they can make those bent screens for you. So a number of years ago, this was a real problem, particularly when it comes to motion, because if you want to study visual motion, right, and you want to study your visual process, there's stuff happening out here, right? And when you think about your visual space, you think about that as like a globe, right? And it's rounded. It's not flat. If you put a flat screen in front of you, what can you see? Edges, right? You can see the edges. They don't make a screen that's shaped like your visual field, right? Now it could cover your entire visual field. They do, but you gotta put it right up there. So there was, I know this because I talked to some folks who make like planetarium projectors. So I was really interested for a while in making a curved display. The problem is with curved displays, the real issue you run into is distortion, like in the bins, right? And so this was a real hard engineering problem to get people to solve, even 5 or 10 years ago, right? So how recently have bent screens been a thing? It's in the last few years. It's not it's not been something that's been going on for a long time. It's easier to do with a projector, I think, than it is like an actual display screen. That's why you would have like those like Omnimax theaters have been around a while, but they're using a projector and they have special technology to like change the way things are displayed on the edges. So it's a good question. Are you thinking about buying a bent screen?
Yeah, they're all going on sale now.
Yeah. As soon as something. Remember those 3D TVs? Yeah. Who wasted their money on one of those? A lot of people. Well, not enough people, I guess. They'd still be around. So so technology changes. This display technology changes, and that's exciting, right? Anybody remember the first TVs ever created? Remember how many color guns those had? They had none. It was in black and white, right? People didn't even think about broadcasting in color. I guess not until Judy Garland did people think we should put color on film. Wizard of Oz was first film in color, in case you're wondering why. Judy Garland was, which they used it very effectively in that film. So, there you go. Color diagram. You know your coordinates. You know where to go. Not a big deal, right? we're going to put a new title on this slide. Cone excitation ratios. That's how this Metamer system works, right? So when you're looking at something that you perceive as red, not surprisingly, the cones that are sensitive to those long wavelengths of light are excited quite a bit. Some of the other cones get excited too. Remember that concept of univariance? You can squeeze a photon in here and there, right? You can get stuff excited. Okay? It's just what is most excited by that wavelength of light, right? What's most likely to be excited. So in this case, it's the I'm not going to get really mad if you call them red cones. I'm going to get a little irritated. So we'll call them long wavelength cones, right? So they're the long wavelength cones. We get a little bit here for those medium, and then the short, not as excited. If we perceive something as green, it's the same story, right? A different cone type, the medium wavelength sensitive cone, is the one that gets the most excited. The other two cone types, not quite as much, right? Not quite as excited. If we want to look at yellow, what's interesting is we see the long and the medium wavelength cones are equally excited, and the blue's a little bit excited. Okay, so that's just the pure wavelength, one wavelength, right? What happens if we mix red and green? What color do we get? We get yellow. Okay, that's what we see. What's interesting is when you mix red and green, obviously the long wavelength and those medium wavelength cones are going to be really excited by that, right? But look what happens when they're excited at the same ratio as they were when they just saw the yellow. You perceive that as the same color, because cone excitation ratios is what drives this perceptual process, right? It doesn't matter what combination of wavelengths of light I use to create that light source, that color. It's what set of cones are getting excited and how much more are they getting excited than the other cones, right? That's what we're going to see. Does that make sense? Okay. Again, metamers are identical because they create that same pattern of firing. They create that same excitation ratio, right? Whether it's one wavelength or two or three wavelengths. Okay. This does support what we call the trichromatic theory of color vision. What's really interesting is this guy George Palmer, back in 1777, had an idea about trichromatic color vision. He doesn't get much credit for it. Most of the folks that do are going to be Helmholtz. He's a big glory hog. Hermann von Helmholtz there. He gets credit for everything. He did a lot of amazing stuff, so he should get credit for it. But we should always go back to George Palmer and give him full credit for what he had. With these other guys too, James Clerk Maxwell and Thomas Young, they both had some trichromatic color vision theories as well. So what we've done now since then, right, we've actually been able to look into people's eyes, I guess, right, more deeply. We've been able to examine the cone types that you have. We can actually look at the sort of genetic makeup of those cones, right? And we know that there are three different cone types, right, that are sort of responsive to the red, green, and blue portions of that visual spectrum. Okay. The other guys were just guessing. They were guessing based on the way these metamers worked, the way other sort of color vision processes worked from the outside, right? Other behavioral tests they could give you. They guessed that there were three cone types. Now we know there are three cone types. And we actually know, at least sort of, how to fix that if you don't have all three cone types. There's some guys out in Washington State who a few years ago, they actually figured out how to give squirrel monkeys color vision. That's pretty exciting. So squirrel monkeys have some color vision. They're a primate. A lot of primates have some sort of color vision, maybe not exactly like what we have. But just like humans, some squirrel monkeys are also born without color vision, right? They're born colorblind. So there was a husband and wife couple. The husband was a visual neuroscientist, and the wife was like a molecular geneticist. And so they figured out how to give color vision to these squirrel monkeys, and so they could pass color vision tests after they had used some gene therapy techniques. One of the few times gene therapy actually works on something. Typically, it's not an effective approach. I think they did it in a dog too. So you never know, right? Pretty soon, everybody will have great color vision. I'm waiting on them to add in the UV lights, like so I can see UV patterns of light. That's gonna be exciting. I'll know exactly when I'm getting too much sun radiation, so I'll be able to see it. You guys want to hear a fun story about birds and bees? So, why is it birds and bees? Have you ever thought about that? Like, have you ever really thought about that for just a moment? Like, how does that even work with a bird and a bee? Like, I've tried to think about this. I never got very far.
Rebecca, I say both like penetrate stuff because bees penetrate like flowers.
Yeah, I understand that, but
And birds like penetrate around different forms and stuff.
but there's got to be some part of that that's a trap too, right? I mean, there's not just the, I don't know.
My mom described it as rockets in the craters, and I was like, this is really awful.
Yeah, that's pretty bad. I guess we know why you're not going into NASA. It's like, nope, not going to be an astronaut now. Thanks, Mom. Ruined that career. So let's talk about birds and bees in a much more literal sense than that. Birds and bees, at least some species of birds and some species of insects other than bees, actually are sensitive to UV light. Okay, UV light's just on one end of that spectrum. It's just a bit beyond what we can see. The only reason we can't see it is because we don't have a cone type, like a photoreceptor, that's sensitive to that wavelength of light, right? If we had a cone that was sensitive to UV light, we would be able to see UV light. What's really interesting is when you look at some flowers, and they look to us just like very plain flowers, if you photograph those using some fancy techniques where you can visualize the UV light, what you see are really interesting patterns so that they can attract birds, bees, other pollinators to that. So those pollinators that are sensitive to UV light, they can see that, whoa, that's like a really exciting flower. We just see it as like, well, it's one solid color. That's not terribly exciting, but it's sensitive to UV light. So that's pretty cool. On the other end of that, so the UV light's actually a little, it's shorter wavelength because it's higher energy. The shorter the wavelength, the higher the energy, right? So as you move past 400 nanometers, smaller, 300, 200, and so forth, you go on down, that gets more and more energy, right? So UV's that way. It's ultraviolet. So if you think about blue being, and then violet, and just keep moving. On the other end of this spectrum, we have what's called, the other end of our sliver of the spectrum, because it's a small sliver, we have infrared, right? So we have the red wavelengths that are at that 700 nanometers. How many of you know things about things that are infrared? We typically think about it as heat, right? Something that's infrared. Your television remote control might run on infrared signals. Some of them do, some of them don't. If it has a little, looks like a little Christmas light at the end of your remote, right? Anybody have a remote that's got a Christmas light at the end? Yeah, that's because that's an infrared light source. So it shoots out a light. Previous remote controls, like the first versions, used like ultrasonic sounds to change, and it would occasionally upset people's pets. You can hear things, and so they went to the infrared. Now, we have different signaling technology now. Think about Bluetooth, for example. You don't need a line of sight for a Bluetooth device to work. Obviously, if you go on the other side of a thick concrete wall, your Bluetooth device isn't perfect, but you don't have to have that UV, or that red light source, ultraviolet or infrared light source pointed at it. If you look at your remote that has that Christmas light on the end, obviously if you point it at your TV, that works. If you were to take electrical tape and cover that, your remote would never work again. Sometimes if you're, I don't know, I'm sure you all have a couch next to the TV, and if you're lying a certain way, you can't really get the remote in the right place, right? But if you just turn that remote and kind of reflect it off a picture on the wall, anybody ever done this one? You can, oh, I do that all the time. So that's how I decorate my house. Like, where am I putting the reflective surfaces so I don't have to get up to change the channel? You can do that sometimes. It's kind of an interesting experiment to try at home. So infrared is exciting. How many of you have heard of pit vipers? These are great. Why they call them pit vipers? If you put them in a pit and throw people in there, it's a fun time. No, the reason we call them pit vipers is just kind of back on their head. They have these little pits that are actually sensitive to infrared energy, to infrared light, and they can see using that, right? So they kind of have a heat tracker system built in. There's a guy in Germany who does research on animals that have weird sensory capabilities, and he uses pit vipers. And so one of the things he will do is he'll wrap the pit viper's head in electrical tape so that it covers its eyes. I know, Deja, this sounds like a job for you, right? Definitely love putting electrical tape on a snake head. And then he puts the snake back in the cage, and that's a very delicate process. I think you just chuck it and go. And then he'll put a rat in there. Here's kind of the spoiler alert. Snakes eat rats, just a heads up. The problem is, if the snake can't see the rat, how's it going to attack the rat, right? That's not really going to work. But those pit vipers can still very accurately attack the rats, even when their eyes are closed or covered with electrical tape, because of those infrared sensitive pits. They get like a heat map of the space around them, and they can track down the food.
Slightly related. Do you know if they inject or have injected in human eyes and give them night vision? I've not heard of that.
That sounds exciting.
That's exciting.
How long does that work?
I think he said hours.
Really? And they just right in the eye?
Yeah, like complete pitch black, 50 meters.
Really?
It's like you're good.
Huh.
But you have to have needles in your eyes, so
Hmm.
I'm out.
Yeah, but I mean, I'm thinking of all the things I'd like to see in the dark. That's exciting. I don't know. Is it aluminum foil? That's what I would put in my eye if I wanted night vision, was aluminum foil. And the reason I would do that is because that's sort of what's in the eyes of nocturnal animals. They've got that tapetum on the back that can reflect the light back. I don't think it would work that way. I don't know. That's pretty crazy. Yeah. We should try it.
Al's got some.
Yes. Yeah. Yeah. I mean, that's how owls are crazy. You got to watch for owls because they're so quiet. They'll eat you before you know it. Have you ever really seen an owl fly? I mean, if you've been out and an owl flies by you, the only way you'll know it is after they're gone. You've just peed your pants because you were scared by something. Because you'll never hear it because the way their feathers are built, they're silent. And then the mouse is gone. But yeah, they have any animal that you shine a light in its eyes and you get a reflection back, it's got the tapetum on there. And that's a quick way to check. You can do that with people. You don't get a reflection.
Is that why your dog sometimes looks really horrifying if, like, you shine a light at them?
That's rabies. Yeah, no, that's why. That's why. Same thing with your cat. Also rabies. Yeah. So any animal that's going to have, you see those eyes and they're just kind of out in a field somewhere. Probably a skunk. Apparently it's skunk mating season right now, which explains a lot of my unpleasant commutes. I'd noticed a lot of skunks. I'm like, wow, there's a lot of skunks. And then I see a news article, it's skunk mating season. So I know, right, Laura? Google knows me so well.
It really does.
It does. So, we talked about pit vipers. We talked about birds and bees. You guys are learning all kinds of great things today. Let's talk about part of me wants to talk to you about the dual process theory. part of me knows you're going to get confused by it, and then there's a part of me that's going to be really excited that you're confused. So I'm going to tell you about it anyway. That's like 2 yes votes and 1 no vote, so I go for it. What I want you to take away from this is, because, what was that called again? I'm just going to write it down one more time. Because we're worried about cone excitation ratios, right? I don't really care how excited one single cone type gets. I don't care how excited all of my red cones get, right? I care how excited they get compared to how excited those medium wavelength cones get, right? And so what I need to do is I need to compare these, right? So let me compare those reds and greens, okay? Let me compare that so I can figure out, hey, red's getting really excited, green's not. I bet I'm looking at an apple, right? It's a great example of something red, although also could be green, right? So it wasn't the best example. So we want to compare that. So we have this sort of opponent process, which we're going to talk about in a few minutes, right? But we're always thinking about not what is this one cone type doing, but what is it doing in relation to the other 2 cone types, right? What are all 3 cone types doing? So we need to be able to pool that information and compare it. So we have that red-green wired up this way. If we want to think about yellow, right, how do we do that? We want to add the blue, or subtract the blue rather, from the red and the green that we've added together. Okay, so we've got different sorts of channels here. We've wired things differently, right? So we're collecting different types of information and we're comparing that, right, to the other information that's coming in. Okay, does that make sense? It's kind of like, you got to think about, we already thought about home runs, right? Let's think about money for a few moments, right? Let's say you want to make $100,000 a year. That seems like a decent amount of money, right? What if you made $100,000 a year in 1948? Yeah, that's like a whole lot of money, right? Or if you got paid $30,000 a year in 1948, you might have been doing pretty good. If you get paid $30,000 a year now, you're not doing pretty good, right? Yeah, that face right there. That's I like that. Should draw that. Yeah. Self-portrait. So we want to think about those excitation ratios. What are the other people around you doing, right? Okay. Here's some more complicated stuff on that we do want to think about briefly. So that first stage is what we call that trichromatic stage. The second stage is that those opposing colors. That's how we get the yellow. Remember before I said we don't have a yellow cone type, right? We get it by wiring up the other cone types. So that's why it's dual process. Straight trichromatic, then we wire those guys up, and we're looking at that, okay? This helps explain why we have certain certain types of color blindness, the most common being red-green, right? So the reds and the greens are wired up together, so if one of those goes out, you're not going to really know what the other one's doing. They're also very similar genetically. We'll think about that in a few moments. All right. Let's think about some color interactions. This is kind of exciting. We talked about contrast a couple weeks ago, right? You guys did that contrast lab, and we said that was really thinking about the dark and the light, right? And there are some classic sort of contrast illusions, right? The checkerboard with the cylinder, and you're like, which one's darker? And they're both the same, right? Even though one appears to you lighter or darker because of the contrast, right? And so if you look at this pair of squares, and you were to look at those green dots, if you were to say which one of those green dots is more intense, is more green, right? Probably the bottom, but it's because of the contrast around it, right? Okay, contrast makes a difference. In fact, they're really the same, and we're doing it here as well, right? So because we've surrounded here at the top a green dot with green or a blue dot with blue, the color kind of fades out a little bit. Here on the bottom, where we've surrounded it with orange and yellow, it's going to stand out more, right? And I think this is a particularly fascinating example of that. If you follow, we have kind of an orange and purple, and then we have a nice teal ring going around that. It may not recreate itself very well on the screen here because it doesn't look that good when I look at it, but I'm also very close to it. If you look at it and you follow that teal ring all the way around, right, it's actually the same color all the way around, but in different segments, I know, right, you don't believe me. In different segments, it's flanked by either the purple or the orange, and it makes it appear different. If you are to see if I can help you here. Oh. You see now how, yeah, it's pretty cool, right? And if I were to do that all the way around, which I'm not, you can see that I could extend that teal color. I don't know what the problem is there. You can see how it keeps going. It's just color contrast. Pretty exciting, right? So there you go. How can you apply this to your real life? If you want to look awesome, hang around a couple loser friends. Don't hang around your coolest friends, right? Because then you look like the loser by comparison. Does that work for everyone? I mean, that's pretty good advice, right? Now you're trying to figure out if you're the cool or the loser friend in your group, right? Like, why does this guy keep wanting to hang around me all the time? I got it now. I am so hopeful that this will play. If it does not, well, we'll see. Wait. I didn't mean to do that. Let's see if this will. Laura, what do you think? You think it's going to work? Oh. All right. Huh?
I had very low.
You had very low hope for this? Really?
You've not had the best luck with.
I've not. Yeah, remember that time I blew a fuse in here?
Yeah.
Or an amp? Yeah, that was something. Okay. So it's not going to work. We might be able to later locate an optical illusion that's similar to this. Essentially what happens is this blank space kind of jumps in this direction, right? And this blank space jumps in this direction. And what you see when you watch this, if you stare at that red dot, is actually when the green square goes off, you'll see the magenta color jump. I know. When it works, it's thrilling. It'll jump in there, and then the reverse will happen here, and then you'll have these two chasing dots. We may, once we finish these slides, is this class over at 1:45? No, got 12 minutes. And we're probably not going to do it today. Someday in the future, so you should show up every day because you don't know when I'm going to do this, except it's going to be the last week. We're going to look at some cool optical illusions online from this great website from this guy named Michael Bach, who's in Germany. Not the same guy who tapes the snake eyes. It's a different guy. But we'll see something similar. Okay, but you get the idea, right? Oh, well, maybe this will work. Maybe I can just go to this website. No, I can't even click on it. All right, brilliant. Okay, so next slide. What about adaptation? Right, that's actually kind of important. If you look at something, right, you guys have probably seen this. If you look at something red for a long time, right, what's going to happen is those red cones are going to get tired. And then when you look away, what's going to be still there are the opposite, right, the green cones. And so you can look at something that's red and then look at a white space, and then you'll see something that's green. We're going to do something like that Thursday, right? So we've got we can pull up some color adaptation things to add in so you guys can see. That's going to be exciting. We're going to have, how many of you love Transformers? Despite deep protestations from one of my,
I didn't protest it. I just thought it was funny.
I've got an Optimus Prime mask you're going to wear with colored lenses. It's not yet complete, but Josh promises me he's going to get it done. It's going to be exciting.
I don't think those words came out of my mouth, but yeah.
Well, that's what I heard. It's going to be exciting. So we'll do this. Basically, what you're going to do is you're going to wear like a set of glasses with like a blue and a red lens, right? And then when you pull that off, you can, especially in this room, it works well because everything around you is white, right? And so you can look at the walls and you're going to go like, why is the wall blue now? And that was the lens that was red, right? Because it's kind of exhausted all of your red cones there, and then the opposite's going to happen the other. Works with like 3D glasses, like the old school 3D glasses, not the new school 3D glasses. How it works. All right. Man, somebody's been saying this like a lot lately. I've been hearing it. It's really like trending on social media, I think, cone excitation ratios, hashtag CER. We're going to get this going. You guys get that trending. Put that on all your Instagram and Snapchat posts. I don't know, whatever, who knows what the new one is. There's always some new one, I never know what it is. And then I find out it's a security alert, and I'm like, great, I didn't have it anyway. So, cone excitation ratios. How does this work? Exactly as I've been telling you, right? It's not important what one cone's doing, it's important what the surrounding cones are doing. So if you look at this, here you get a lot of green. So because you get a lot of green going on around it, and you look at that little bit of green in the inside, well, not that much. But over here, because you're mostly getting a red response, then you get some green. That green's going to pop out, right? Because it's the excitation ratio, okay? All right, what else do we want to think about here? When you already know this, right? Reflectance is sort of a property of the surface, right? Okay, we talked about that with contrast, right? When you calculated that contrast, it's not a perfect lab, but a lot of times you should get similar values, right? It doesn't matter what the light is. It's going to be quite similar. But what's interesting with color is we get something called color constancy, right? Because when you use different types of light onto a surface, you do get globally things that look different, right? But within that image, everything still kind of looks the same, right? And so if you pick out this lime, for example, that's what that fruit is for those of you that don't know limes. Limes are green, typically, if you know, it's when they're good. But if you look in each of these three images, the lime is still green, right? And it's still relatively the same green compared to the rest of each of these images. But when you look across the three images, you can see that things are different. This represents artificial light. Here we have daylight in the middle, and this is a clear blue sky. Okay? So you can kind of see how things look different in different lighting conditions, but the color constancy is still there, right? That's why grass is always green. Doesn't matter if it's noon, doesn't matter if it's the evening time, you know, it's still going to be green, right? Even at night, it appears green to you, as long as there's some light coming to you. Okay. There are important things we need to think about sometimes with like taking pictures and films, right? Because they don't have any constancy mechanisms, right? So when you do take an image, that color will change. Anybody into photography? Yeah, right. So lighting is very important, right? If you change the lighting, you can really change the way the image looks quite a bit. You can take a picture of the same object, change the lighting conditions, and that can change. Your camera doesn't do what your brain does. I don't know. No, it's a shock, right? There's so much more going on. Okay. Let's talk about color deficiency a bit, right? There are basically a couple ways that you can get color deficiencies, okay? And we're thinking about in the retina here. We're not thinking about higher order color issues. You can be missing an entire cone type or cone types, you know, up to 3. Or you can have those cone types, but maybe one or more of them's just a little bit off, right? Okay, so it's not perfectly hitting that medium wavelength. Maybe it's shifted one direction or the other, and it can give you some interesting sort of things to think about, right? Because when you think about these color spectra, right? So if you were to draw let's get out of this. Yes, I want this whiteboard. And who knows what's going to be on here. Yep. You don't need to pay attention to this, but I need to draw something for you in the next 5 minutes. Clear. Where's the clear button? Clear canvas. Okay. So, if you were to draw, let's do a, right? And this is going to be response on this side. And this is going to be wavelength. And as we move from, we're just going to do, well, we could do 300 to 800, right? Whatever. We should probably actually go up to 1,000 and do 200. What you would see is down here is kind of your short wavelength cones. That's where they get really excited. They get that peak response kind of right there, right? Your greens shifted over here. And then your reds, what's really interesting about your reds, okay, let's put those there. Notice how close these two peaks are, right, in those cone types. They're both really testing for the same thing, something very, very similar, right? And so if this green guy is just a little, if that photopigment's just tweaked a little, we can shift its sensitivity closer to red. And so now, that peak is shifted over, right? It's shifted to here. And it's much closer to that red peak. And because it's closer to the red peak, guess what happens? When the green cone gets excited, the red cone gets excited too. And when they're both excited, their excitation ratio is similar. And if their excitation ratio is similar, then you think, I'm seeing something that's both of these. That's why the red-green color blindness is most common, right? Because it doesn't take much of a shift. To get your blue, you'd have to really screw up your blue, right? Because, I mean, you'd have to shift your blue like all the way over here, okay? That's several hundred nanometers. You're not going to do that, right? We're talking maybe a 50 nanometer shift in the green to give you some problems with the red. Folks who are red-green colorblind can't tell the difference between red and greens. They typically see both of these as some sort of brown. Reds, greens, and browns all sort of look the same to people who are red-green colorblind, right? Does anybody know somebody who's red-green colorblind? Yeah, I mean, it's not rare, right? I'm not going to say it's common, but it's not rare. Probably a male, is that correct? Most females, because it's a sex-linked, right? If you get two X's, that's pretty awesome. If you've got one that's screwed up, you can just use the other one, right? But if you've got an X and a Y, I got to tell you, you got to use an X. You can't live without an X. Okay, you got to have at least one X. Okay, you can do without this other one over here. But if you only have one X and that's got the little screwed up part on it, guess what? You got to use it. Okay, and that's why males are much more likely to be colorblind than females. For a female, you have to have two screwed up X's, right? And then you've got no choice but to use the one that makes you colorblind. Does that make sense to everybody? Okay. Now let's just make sure, is there anything else we want to talk about here? And I don't think so. All right. That Thursday, we're going to do color blindness tests.